We are on now to our last discussion for today, and we can focus a little bit on the talks that happened after the earlier discussion, but really any presentation or topic is up for discussion. And reminder that kind of after the end of formal discussion here, which will be, whenever it all seems like it's kind of stopped, we'll have a more informal session for just conversation and networking. So please stay on for that. Grab yourself a drink if it's that time of day for you, and you like that kind of thing. And then this will just kind of be open as late as that wants to go, as far as my understanding goes. So thanks again to everybody, and just anybody who wants to talk, raise your hand, put in the chat, start your video.
So there was already a question in here for the discussion that relates to the earlier talk about the CTX automated change detection. So Avinash Das, sorry if I mispronounced that, for the automated crater detection, what are the key parameters taken into account for establishing an algorithm or a model? So I don't know if the speaker is still here, or
that
if
would
maybe
be Michael Monge. Are you still on?
doesn't look like it. I don't know if Ingrid, are you able to answer that at all?
I'm still on, but I'm sorry, I don't know enough about Michael's model to answer that. I think he'd be the best one to answer.
All right. In that case, sorry about that. But I know that they had a follow-up, so I'm going to go ahead and unmute you. And you can ask your follow-up question, which was more towards a discussion of planetary science in general and skill sets. So you should be unmuted.
So just related to that, I'm sorry, but I don't see a button to raise my hand. I'm using a Mac, and I think perhaps this feature is not available for Mac.
It is, because I'm on a Mac too, and I see it when I'm not a co-host. So I think because you might have been made a co-host so that you could present, you probably don't see it, because it goes away magically for some reason.
Okay, thanks.
Hello. Am I audible?
Yes.
Yeah. Good evening to all. My question, as a fresher to planetary science, what are the skill sets required for working in planetary science in general, and what are the skill sets required for crater detection in particular? I am particularly a person from geology and remote sensing background. So if you could shed some light on it. Thank you. Hello.
So who wants to take that? What skills do you need for working in planetary science, and potentially for automated crater detection and other stuff? Looks like a lot of people responded by a lot. That would be one person. Nope, no one responded in the text box about that. I don't know, Michelle, you've been in this slightly longer than I. Maybe you can say something while we wait for other people to chime in, like Clark, Bill McKinnon, or other people who have been around for a few years.
Paul Shanks has a thick skin, which is probably true, particularly in the cratering field. Yeah, I think it does depend on what you want to study, what educational background you need. A lot of people come from geology, so I think that's certainly reasonable. And you just, if you find you're interested in planetary, find somebody to work with, hopefully, that can get you going on a project with the skills you already have. Or if you're interested in something different than the skills you have, then, go out there and find the skills, way to get the skills you need to do what you'd like to do. there's certainly been a variety of skills shown today, from numerical modeling to observational geological kind of work. So yeah, and as Paul says, determination and passion also really help, I think. That's kind of my point of view. I got into it from physics, and I got here because I was doing physics and astronomy, and I was like, but planets are cool and geology is cool. So I decided to explore planetary science further because of that. And other people who have been in the field, please speak up.
I don't know if I count as in the field yet, trying, but what I find really helps is finding somebody to work with. So find a mentor or find somebody who's already doing what you want to do and help them do it.
I guess since no one else is speaking specifically, although Jamie says from an outsider's perspective, you have to be a little crazy. Yeah, maybe. So I would say I was originally going to go into electrical engineering because they made a lot of money when I was looking at colleges. And then I decided that I don't like electricity. So I just went with my hobby, and my hobby had been astronomy. And so I went through a classical astronomy astrophysics training and then went to grad school for planetary because I didn't like the big numbers. I liked the idea that I could actually send a spacecraft to where I wanted to study. And so I sort of came through an astrophysics and then sort of planetary geology background, not through geology, which a lot of people in planetary science do. But as Michelle said, I mean, just today, a lot of different skills have been demonstrated, anywhere from geology to physics to being able to count and draw circles, to computer science. We had dynamical simulations in at least 2 talks, and then of course computer vision. So I don't know if Michael Clear is still on, but he's sort of was an undergraduate in astronomy, but then really more computer science. I'm sorry, astronomy was a minor, and he's been working with a few of us over the last 2 or 3 years on automated crater detection. So I think I mentioned to you privately, oftentimes if something requires a very specific skill set that is sort of outside of planetary, usually you focus on that skill set and then partner with someone who's in planetary to work on it, but you don't have to. It's just might be hard to maintain all that specialty inside of your head. And with that said, Clark looks like he wants to be unmuted, and it looks like he is unmuted, and so he can chime in as well.
Well, I've been around in this field for quite a while. It's a very interdisciplinary field. So you can come into it from chemistry or physics or astronomy or geology, any of that. If you're going to count craters, so you have to have a lot of patience. And a number of the people at this meeting do that, and that can get a little boring after counting thousands or tens of thousands of craters, or as Stuart has done, millions of craters. So just thought I'd mention that.
And I've gone ahead and unmuted Cassie. Cassie, if you want to chime in so I don't have to read your comment.
Oh, yeah, absolutely. So I was just going to say, like, if you can hear me, I hope that I am now unmuted. Yeah, looks like it.
Yep.
Just in terms of more concrete skills, I know I was in a group in graduate school that was mostly a radar remote sensing group, and I sort of got into thinking about impact cratering sort of more on my own. And some of the things I had to pick up on by myself, were more like learning how to use the PDS, finding various data sets and being able to download those and look at them and analyze them. At the time when I was in graduate school, I was writing a lot of my own sort of stuff to analyze that in IDL and using ISIS-3 and things by hand, but there are great tools now like JMARS that you can go and use to do a lot of that stuff without having to write it from scratch. So that would also be part of my recommendation, is go and look up those tools so that you can sort of get your hands on the data yourself and sort of see if playing around with it is something that interests you.
It looks like Michael Clear added that, yeah, machine learning is a whole huge rabbit hole, but there's a lot of resources out there for improving machine learning skills. I don't know if those resources would necessarily be understandable from someone with my background, but yeah, I mean, and as Cassie said, I also do a lot of programming. Right now, it's 90% of what I do. But you don't have to. And Jamie Riggs, who's on the executive council, has been to these for now 5 years or so, and she's not a creator person, she's a statistician. And so she sort of partnered with me and then spread her wings and worked with more of us to really add her skills to the analysis. So as Clark said, it's very interdisciplinary. And Michael just turned on his camera, so looks like you're unmuted too, if you want to chime in a little bit there.
Yeah. Okay. Thanks for unmuting me. Yes, my name is Michael Clear, and as Stuart mentioned, I've been working with this group for a few years. Just adding, I did my undergraduate work in astronomy, and I've since moved into machine learning and sort of the industry field, but I've been continuing to do some astronomy work as a hobby. So I could just say that in general, any of this type of work, you definitely want to get comfortable getting your hands on computer science and data management skills. Those skills are really applicable. You just have to be really focused about, I guess, your intentions and not be afraid to get into sort of learning new things. I know that's really generic what I'm saying, but I think in general, just having at least some background in computer science and some skills manipulating and handling data will be helpful for any sort of niche that you find in planetary science.
Yeah, and Matthew Huber, sorry, I'm sure I butchered your last name, wrote that from the terrestrial side of quote-unquote planetary, it is not necessary to ever do crater counting if you're not a fan of circles. So yeah, there's also so you can just be a geologist on Earth and study craters. David Kring at LPI does that, and I think Don Burt is going to be talking, plus a lot of people at USGS, Tennille Gaitner, I'm sorry again if I mispronounced the name, they do field work. Joe Boyce, huge in cratering, really cut his teeth on field work. And then Gunther, I'm sorry, I'm not going to try to pronounce your name.
Hey, Stuart, hold on
Yeah,
a second. I unmuted Matthew Huber, and if he would like to say more about the terrestrial side of things, because that is a perspective we don't get super often. So, Matthew, would you like to speak a little?
Sure, I guess so. I think on Friday we're going to have a little session and talk a little bit about terrestrial impact craters. These impact craters that everybody's talking about for this entire meeting, we can actually go out in the field and look at them and actually physically touch all of these objects. And this is what I do from a geology background, and it's pretty much using just standard geological techniques, geochemistry, petrography, structural measurements of the craters in a very classical geological sense, except applying it to these objects that are only formed as a result of solar system processes.
Cool, thanks.
Not sure how much else to add there, but it's very interesting. I think the comparative planetology, I think, is a very important aspect of this. And it's something that I'm always cognizant of when I'm looking at the craters on Earth, that these are sort of the key to understanding craters on other planets, but at the same time, the craters on other planets are also helping us to understand the craters on Earth. So, yeah.
Yeah, that's great. Thanks.
I think that sort of a summary would be that you can sort of approach it from anything you want. And unless it's like way out there, like you're in business and got an MBA, then I think almost anything you have can be relevant. there's another topic if we want to move on. And Kush wrote, is there any correlation of crater density on airless bodies with respect to their distance from the sun? So I think the general answer is yes. I don't know if it looks like Abedin, good, just unmuted, and I think can respond to that better and more completely than I.
Yes, the short answer is yes. There is a correlation with the heliocentric distance. Though, so the reason for that is because it essentially depends on the spatial density of the objects. If you took, for example, the asteroid belt, and if you count the number of objects in a unit volume, you will have more objects compared to the Kuiper belt, for example. This is kind of the short answer to it. And well, if you want to calculate the collision probabilities, it will, like the number of cratering, the number of craters that you would have on a body. It would also depend on the orbital distribution of the objects, if they can intersect that target.
And the velocities vary
and the
a whole
velocity.
lot.
That is right.
Distance from
That is right. That is correct. And the velocity.
So Gunther also had a question a little bit earlier. Said crater frequency may be sensitive to the porosity of the impactor. As the impactor approaches, it may fragment before impacting, leading to multiple impacts. Does crater counting try to reflect this mode of impacting? It looks like Gunther came up, so I'll unmute you. So.
Hello, everyone. It's just a simple question that I consider. For me, it's important because I'm trying to think of the very, the bodies that are kind of rubble piles, and as they approach the high gradient gravity field, they may just split in multiple impactors before they impact.
Yeah, that's not really generally right. Shoemaker-Levy 9 comet was tidally disrupted by Jupiter, but there are papers that explain the possibility of tidal disruption by the Earth and so on, and it's just very rare. So there's, you can disrupt coming through the atmosphere, but of course the dispersion is very little. So you get clusters of tiny craters on Mars, but basically you can't get much effective disintegration during the few seconds and impactors in the atmosphere. Comets, very small comets that have negligible gravity can disintegrate in the inner solar system from time to time. Several have this year, but disintegration doesn't generally happen.
Thank you very much for your insight.
I actually have another maybe topic for discussion very quickly if we have time. I would like to know how well do we understand cratering on cometary-like bodies? Do we have other laboratory experiments aside from the deep impact mission? And to clarify that, I'm mostly interested in if we shoot a bullet into a cometary-like object, what would be the size distribution of material? And it's getting even more complex here because I think the material, the ejecta, will be, so to say, a mixture of ice and dust. So is the ice still coupled to the dust, or is it going to produce icy particles and dust particles separately, because immediately after the impact, all the material is just a vapor, right? Depending on the energy of the impact. If someone could clarify or elaborate a little bit, how well do we know these processes at the moment, that would be great. Thank you.
While other people might be finding their fingers typing or finding the unmute button, or raising their hand, I'll just say I don't think we understand it very well at all. Because if you look at what people have reported for craters on comets, they vary considerably, and they vary based on the comet. So a couple of us did a review paper in 2018 on crater depths, and we looked at all the literature, and you see things that look very obvious like craters on like Comet Wild 2, but then you see craters on another comet which just look like deep pits, and we don't know if those are craters or not. So if they are, then the depths are ridiculously deep, but if they aren't, then it doesn't have craters. And so I don't really know. And you brought up deep impact. I know there was a lot of actual lab work done in preparation for deep impact, but I don't know if there's been any lab work since.
Yeah, I've been digging through the literature about this to find kind of more recent work on what really is going on. I see that Bill McKinnon said in the chat that the density of the of the comet surface is a critical parameter. So I guess perhaps, I don't know if we could simulate a comet in a lab and do like some experiments and derive some scaling laws, particularly for these kind of materials. Yeah, I know. I'm sorry, guys.
Yeah, it looked like Emily also added something that L-Cross impacted into it, ice regolith mixture that produced both dust and a volatile plume. Maybe a useful analog. I can.
Yeah, I could probably discuss this with Emily later. I could get her email, and because I'm at a stage where I mean, in my research, where I need to understand or to dig out all the information that we know about collisions between cometary bodies.
Cool. Well, it looked like Matthew Huber had a question. Instead of reading it, I'm going to just unmute him so that he can ask it himself and start the conversation. There you go, Matthew.
Yeah, in the talk, looking at the mare on the moon, there was the ages of various parts of the lavas were dated, and if I was reading correctly, it's more than 1 billion years difference from the youngest to the oldest. But if I understood correctly, the chemical composition doesn't seem to change that much between the terrains. And so I'm not clear, is that suggesting that you have a magma source that's either being replenished or staying consistent? Or does that mean that something is questionable about the dating? Or how should we interpret that?
Good question. Is Thomas still on? Doesn't look like it. Anybody, any other lunar experts want to chime in about that?
Sorry, I wasn't paying entire attention. I'm sorry. What was what was the question?
Hi, Lillian.
Hi,
The question.
Matthew. I'm sorry, I wasn't. It's been such a long day already.
It's getting close to midnight here, so I
Yeah.
understand. Yeah, so you have this mare that is dated with an age range of something like 1 billion years from the youngest to the oldest, but the chemical composition, particularly the titanium, is staying consistent through the whole process. Is that saying something about the magma source, or is that making the dating questionable?
Well, from my familiarity, and I am not involved with Tom's project at this moment, but from my research and work in Imbrium, it's a combination of those two. Generally speaking, we know that Mare volcanism is long-lived, and most likely because of the long-lived nature of the Mare volcanism, we know that, like in Imbrium, there are very distinct titanium content differences. But one of the things that we always question is the uncertainties of the lunar chronology because of our limited samples. And so personally, I maintain healthy skepticism when it comes to absolute model age dating of Mare units. And so I think it's a combination. Certainly, I think we can have a little bit more faith that model ages derived for the Mare are going to be better constrained than, say, volcanic units on Mercury. I believe the lunar chronology derivation more than I believe the derived Mercury chronology. But within that, there's still wiggle room of hundreds of millions of years that can be accounted for by user uncertainty, user error, as well as the unknowns related to the chronology. So, I think that the other thing is we haven't had a lot of research. I mean, yes, there's Harry's work, there's the new research that's been going on with our more recent lunar data, the higher resolution images from LRO and Kaguya Celine. But I still think, I personally am not entirely certain how small count areas we can go in the Mare and have really representative results when it comes to things like this, the comparative difference of spatial scales of composition versus age derivation, if that makes any sense.
Yeah, thanks for that. That does make sense. I'm wondering. I honestly don't know that much about the Mare process, but if I compare it with large igneous provinces on Earth, those we think most of the time they're being erupted over pretty short periods of time, not even 100 million years in a lot of cases.
Yeah, there were geochemical models. I'm not a geochemist, but there were geochemical models that predicted that the composition of the eruptions would change because of what's going on in the magma chambers. And the data, if they're correct on the ages, would suggest that it doesn't change much. And maybe those models expecting that weren't correct. I of course share Lillian's skepticism about how strongly to adopt the reported ages, but they're probably roughly right. Who knows?
Okay, thanks.
Okay.